Hi, I'm Dr. Christopher Newman. I'm Professor of Space Law and Policy at the University of Northumbria in Newcastle in the United Kingdom. I'm also International Space Law Advisor for Cold Star Technologies. I listen to the Cold Star Project.
This show is for entertainment purposes only and is not intended to be what is termed professional advice. The Cold Star Project is proudly presented by the Operational Excellence Society. Cold Star Tech is a supporter of the OPEX Society, and Jason Kanigan is a member of its board of advisors. Talk with us at Cold Star Tech to find out more about the OPEX Society and what we can achieve together in your organization, or just visit opexsociety.org. Thanks for joining us for today's show. Rick Ward started out as a U.S. Marine, so, he's got to be a good guy based on that, right? And then, after a while, he moved into Deep Space Industries, a company we all remember and love. As, first of all, a chief laboratory researcher, and then being promoted to production manager. And I don't know, if you don't know this circle of people, the DSI folks are really good to know. A lot of experience. They're very realistic about the space industry. They were the non-hypey people, And so Rick comes out of that and has a lot of great connections with that circle. For the last 2.5 years, he has been the CTO and founder of OrbitsEdge, which is all about edge computing in space. And we're going to talk about the journey that he has been on through this period. We did an interview some time back, I'll link to it below, where this idea was new to people. They didn't understand it. It wasn't an idea whose time has come. But now, with the strain on the deep space network and maybe a cislunar economy, we are seeing a need, and other people are seeing a need for edge computing in space. And so perhaps it is time for OrbitsEdge to really kick into high gear. So, Rick, welcome. So, Rick, let's lay out the case for edge computing. Let's define it in terms of space. We're going to talk about the deep space network in a minute, but just let's talk about the concept of edge computing for somebody who's never heard of it before.
Yeah, sure. So on Earth, everybody's familiar with the cloud compute network, which is basically somebody else's computer, as everybody says. But there's places where that's not reasonable for you. Now, there's cloud computing nodes in every major city and many of the minor ones, but not too far away, there's activity that happens that isn't close enough to the cloud for all that data to go back and forth. So that's things like factories, refineries, any sort of resource extraction, any sort of mining or oil or whatever. Farms are getting into the data generation game, which means they're generating more and eventually lots of data. And the idea is it's a burden and also expensive to transmit all that data back and then forth. So it's easier to set up computation where the data is originated.
Mm-hmm.
And here you'll see edge compute scenarios like 10 miles away from cloud nodes, where it's easier and more attractive to set up the compute. When you have the cloud that close, it's still more attractive to not send the information back and forth. So putting that scenario in space operations and space terms, you have a bandwidth down limitation in terms of ground stations. You don't have 24/7 infinite bandwidth down to Earth. You have, here's a ground station, we pass over it, we're going to be in contact with that station for like 1 to 5 minutes or so. Then here's another ground station over here, we're in contact with that one. Oh, wait, there's clouds, there's a storm there, so we're not in contact with that one. Maybe the data got down, maybe it didn't, I don't know. Maybe I have a method of tracking it, maybe I don't. So we have the ability to generate and capture a lot more data than what we can get down to Earth. By doing computation in space, you can do, at the very least, you can do what we call wheat from chaff, where you're just separating out trash, throwing that away, sending down the good stuff. You can also do stuff like change analysis. And we're talking right now mostly for For Earth observation, which is kind of the low-hanging fruit, it's not the best use of this, but it is the best one that exists and is commonly understandable right now. So change analysis, that's where you take a picture, and we're looking at having petabytes of storage. So we've got plenty of room to have a database of previous imagery. You take a picture, you compare it to the previous picture, you see what changed, you crop out the change, send that down, throw away the rest. So you're sending down novel information instead of stuff that you already have. Another one is metadata generation. Nobody's ever going to look at a picture of a parking lot. What if we just turned it into a spreadsheet in space, threw away the image, sent down that? You can send down like thousands of spreadsheets of parking lots for the same bandwidth of one image. So you basically get higher refresh, higher rates of new novel information getting down. You can also do things like object tracking over time. One of the neat things about the change generation, change analysis, is it finds stuff that you didn't know you were interested in, kind of borrowing from the Rumsfeld idea. So the two big news articles of the past year in terms of Earth observation were the Uyghur concentration camps and the missile silos. Both of those would have been picked up as soon as they started rolling trucks out in the middle of the desert, because the trucks are new and weird, and it would have said, for whatever reason, somebody's parking trucks in the middle of the desert. Somebody should look at that. And humans would start looking at it, and that would become a topic of interest pretty darn fast. Now, in terms of what we're really excited about for edge compute is, think about all the stuff that has happened in the use of computation here on Earth in the past relatively few years. And now I'm talking about AI and autonomy, where you have machines doing part of the decision process themselves, where you can have drones delivering things to you or for you, or delivering you for that matter. Imagine if that sort of capability existed in space. Right now in space, satellites can do what they can do because they have the capabilities that they have, which is mostly basically joystick control. Some human down on Earth goes tappity tap and says, this is what I want you to do, and that's what it does. They can upload things prior to, and they can say, at such and such time, I want you to point exactly in the direction of this ground station, send down your information, then I want you to turn towards the Earth and start taking pictures again. Then there's another ground station, and I want you to point towards that one. So with autonomy, you can offload a lot more of that tasking in more of an ad hoc basis for the actual satellite to act as a robot instead of a dumb satellite. There's various companies that are working on manufacturing, assembly. There's even companies working on recycling of space debris. All of that stuff is going to involve generating a lot of data. And if you can consume that data on orbit instead of having to have a permanent relay, which you don't actually have, then you can get more work without overtaxing the bandwidth constraints that exist.
Yeah.
If that wasn't too much of a monologue.
That's what we need, though. That's the education portion of the show, folks. Rick, I really I knew about the mining type thing, right? We would see this on the lunar surface, maybe extracting some soil or regolith or something, and then filtering that. And I like on the Earth, you could put a huge amount of material into a giant truck, drive it to a huge processing plant, and process it there. Or you could have a little machine that processes it on site, and that's kind of what I was thinking about in terms of edge computing. But what you were talking about the transformation of data from, say, a high resolution image to a low spreadsheet, right? Where it's just, we want ones and zeros, ons and offs. So, hey, there's an indicator of a digit here that wasn't here, right?
Yeah, go
And
in
being
the
able
other
to
direction.
transfer that. That's fascinating to me.
Yeah, and it's what it really is about is in that scenario, it's about increasing the overall quality of the data that does come down. So it is saying the average quality of the data is better than without this capability.
Okay.
More new stuff.
Yeah. How are we using it? Right.
Yeah,
right.
we're getting really, really good at capturing and generating data. I mean, in nature, the data is there. It's just a matter of how much of it we capture. So, but what we're interested in is specific scenarios, which means all of this turns into a needle in a haystack problem. And we're getting really, really good at making haystacks, but we're not as good at finding the needles. Right. And computation is what lets us find those needles. We want the needles. We generate the haystack, and every haystack has one or more needles in it, or maybe none sometimes.
Yeah.
It's a matter of how good we can get at finding needles in haystacks. Like the haystack's the easy part.
Right. Yeah, we have a data science department at Cold Star Tech, and we do undirected learning, which is exactly what this is, right? Pulling out the we don't know what we don't know. Tell us, machine learning or AI. What is weird here?
It's easy to say to send a direct query and say, what is 4 times 4? I need the answer to that. That's important to me, but telling me that somebody's about to run out of gas. It is a thing that I did not know I needed to know, but it's suddenly very important. And if you can do it before it actually happens, then it's beneficial to everybody involved.
Right. And you could use this in politics too. Politicians often don't know what they're deciding, right? They can make yes, no decisions, on, off decisions all day long, but most of the time the leaders have no idea exactly what they're deciding, and that's why it's so easy to screw up. So something like this would be very helpful.
And then you've got government by AI, which is might be a portion of a different episode, might be a whole series.
Yeah, that could be. Yeah, that would scare the hell out of a lot of people. But the social engineering and these kinds of concepts are worth discussing.
We talk about AI like it is a black box thing, but really it is a thing made by people. And it has all the biases, intentional and unintentional, that everything we do does. So garbage in, garbage out is a very real part of that. You remember back in the day when they first started putting AIs on the internet and exposing them to human chats, and they go from like sweet, innocent AI to full-blown Nazi in like half an hour.
Right.
That's if it's going to be a two-way street where we interact with it and it interacts with us and it learns from us, well, that's it has to have that discernment.
Yeah. That's a great word. I love that word. It's one of my favorite words, discernment. So we're going to touch on this idea. You brought up the specific applications phrase, right? And so we're going to look at one right now and then go away from it and then come back to other applications. But I want to talk about the Deep Space Network, which has come up a lot in my news feed since I first talked to you about it. I guess it's just that effect where you start filtering it in, right?
Yes.
So we talked before. We did an interview a year and a half, 2 years ago, something like that. And I've watched you, on the journey with this startup, and there's that phrase, nothing has the inevitability of an idea whose time has come, right? And I feel that the idea of edge computing, its time is coming. One area that we're seeing the general opinion change on is that we need to add capability and capacity to the Deep Space Network. Let's talk about what that is, again, for people who have no idea what the DSN is, and what is happening, why expansion of it is so difficult.
Yeah, so, and this is a great place for animations to come in. The Deep Space Network is an array of ground telescopes they provide connectivity between the Earth and all of our probes throughout the solar system. And for one node, you need 3 antennas separated by 120 degrees on the Earth's surface. So one of the origins of the Australian space program is when we set up DSN nodes, the very first DSN nodes for the Apollo missions in Australia, in the US, and somewhere else. Somewhere else that I should probably know by now. But now the modern iterations are, if you can set up 3 nodes that are 120 degrees away from each other on the Earth, you have added one element of capability to the DSN. These nodes go from, like, on the low end, like 10-meter diameter, to as big as you can realistically make them. So if we had like 3 Arecibos, that would be great, but that is really beyond our capability at this point. Well, no, it's not. It's beyond
political will.
How much somebody wants to pay to dig a giant hole in the ground.
Right. Yeah, we don't have the CIA looking to spy on the Soviet Union the way they were in the 60s. Here, have a radio telescope. We just need to use it for an hour once a month.
And fortunately, we don't have 3 mega craters offset on each other by the appropriate amounts. So there's that. There are other craters we could possibly use, but Arecibo is one of the one of the more convenient ones. So that's what the DSN is.
Okay.
In terms of how much we're reliant on it, the inverse square law is not your friend in this scenario. It says that if you double the distance from A to B, from transmit to receive, you have to quadruple the amount of power to get the same signal to the end point. So as you get farther away, all these probes are small and weak. So they're essentially a mouse whispering in the dark, and we have to hear that from millions of miles away. So it's not an easy task. Listening to the Voyager probe send information back, the farther it gets, the slower it has to transmit so that it can be heard. There's a lot of things that can interrupt that dot or dash. So it's not easy to get the data back. So the DSN is highly burdened. We recently added like 3 more probes to Mars. I'm not sure what their lifespan on all of those is, but they will be generating and transmitting data that whole time. We're gonna be flying more stuff to the moon. That's gonna be happening regularly up until we actually send humans back. All that stuff as well. In fact, NASA in their communications with the contractors developing Artemis payloads has said, please do not overly rely on the DSN. Please keep your use of the DSN to a minimum. Try and come up with alternate means of communications and relay. So yeah, this is a problem. And one of the best ways to reduce your reliance on a communications capability is to eat the data at home. So by doing processing, you can reduce the amount of data you send back. As an example, the Curiosity rover, well, that thing traveled hundreds of meters over like 5 years. If that was a mining robot, it probably would have generated a few gallons of propellant in that amount of time, assuming that rate of travel. If you're going to generate a small swimming pool worth of propellant, you need to travel a lot farther than that, a lot faster. So you would have to travel instead of meters per day, you'd have to travel kilometers per day in order to do enough moving to generate the stuff that you need to generate in order to be an economically viable operation. And I'm not necessarily saying that everything has to be moving. Generating methane from Mars is a relatively static thing, but you still have to have rates of production. You have to have rates of intake, and all of that stuff is going to be instrumented. All of that stuff is going to be, well, it's going to be instrumented. It's going to be generating data. So that means the data has to be consumed. And that's what edge compute's about.
All right. So we're about to generate all this data, much more data. What technology do we need? I know you've been looking at radiation hardened processors for a while. Do we have this tech today? What do we need to make a shift to in order to be able to have more edge computing capability?
Yeah, the standard way of doing radiation hardening of compute gear is not really viable going into the future. What you generally do is it's a long drawn out process, can take a decade relatively easily, and you end up with a design that is frozen in time.
Yeah.
So you have a processor that is, if I'd started in 2020, I probably would have looked at some sort of a processor that came out between 2010 and 2015, found the most reliable one, slowed it down, redesigned it, reworked it, did a lot of work to it. I would maybe be comfortable with selling it by 2025. I would, if I'm super fast, people would maybe start trusting me by 2028. And I'd probably sell my last unit in 2050. And I don't really see how that model really carries us significantly farther into the future than what we already have. So what we looked at is, what if instead of doing that, we build the box, the radiation shielding solution, then we do our own thermal management system, and we have something that we call an Overwatch system, which is a rad hard computer that ties into the telemetry generated by the working computer, by the one that does the workloads, and also ties into radiation sensors both on the vehicle, in the vehicle, and external to the vehicle, meaning space weather sensors that are remote and communicate their predictions to interested parties. We tie this Overwatch system into that, and it can provide protection, restart, diagnostic, and some degree of troubleshooting capabilities to allow the computer to operate for about 3 to 5 years.
Okay.
If our radiation shielding, our thermal management, and that system work, then we can essentially provide modern compute capabilities from today into the future, because this is intended to be relatively hardware agnostic. So as we go forward, we can bring in current technology. It is scalable. It is customizable. It's intended to be a future-proof solution, and we're developing this in cooperation with our partners at Hewlett-Packard Enterprise.
Okay, so very interesting. If you take the direction of developing this technology from the chip, right, the processor, the rate of change and user adoption is super slow. So why bother?
It is, and we've done it.
So you adopt a different direction.
Yeah, that's happened. Like there's like a half dozen, well, or more. There's more than a half dozen generations of chips that have been designed and built on this model, and the process gets harder as you go farther along. So chips get the density increases, the complexity increases, and doing this sort of serious re-engineering gets harder as you go farther along.
Okay.
So it's a diminishing returns thing, and that makes sense in terms of this is going to be a 25-year mission, and we need something that will definitely live for 50 years. Because then you don't care as much about new. But if you're looking at something where you can have where 3 to 5 years is an acceptable mission life, well, a 3-year-old computer is significantly different from a brand new one, or a 5-year-old computer is significantly different. But there's no real difference between 20 years and 25 years.
So what form factor does this take? Is this a small sat sized object that it's pretty cheap to throw up there, you know, as itself?
Ish.
Or ish. Because all the things still cost money.
What is cheap in space? So we're looking at our initial form factor of something along the lines of like a college dorm fridge. That's kind of 200 kilos or so. We're also looking at a larger one that would be more of a residential refrigerator.
Okay. And these need to be replaced every 3 to 5 years. So they need a deorbit plan or a recovery plan of some kind. And
absolutely. We're also due to customer acclaim, and this one is trickier because from our perspective, our radiation shielding works better as you get bigger.
Okay.
So that's a question of cube square law.
Yeah.
Where as a thing gets bigger, the amount of surface area relative to the volume gets smaller. So for the size, an elephant has less skin than a mouse. Therefore, the elephant is better at retaining heat. The mouse will freeze to death more easily. So in that sense, there's a point at which we have a harder time guaranteeing life cycles. So, but at the same time, we've had a lot of people ask for this sort of thing. We're looking at a small form factor that's basically a single blade. That'd be like one blade, one CPU, one GPU, maybe 200 and something terabytes of storage, around 200 watts. And this is intended to go into your satellite.
Okay.
So this is just the computation and just compute, radiation and thermal for you to provide power to it and it to work on as a dedicated platform for your workloads. We're doing some studies on radiation shielding to see just what we can guarantee on that. Like I said, that is one where it's more of a customer driven instead of something that we really, really wanted to do. We're also looking at, I mentioned the elephant and the mouse. We're looking at an ARM based architecture, ARM meaning like my cell phone processor. I expected it to come on. Yeah, there it is. My cell phone processor. That is intended to be like around the 10 watts. 10 to 100 watts power requirement. And it is intended to survive the lunar night, assuming that it has some amount of power going into it continuously. That is, we don't expect our first iteration to be fully capable of that, but we expect that by the time we're doing lunar missions, we can deliver something that can survive the lunar night on the scale that our partners will also be working on. Because a lot of these missions, they're exploring how to survive the lunar night. That's not something that's a normal, easy thing to do. So there's a lot of companies that are developing platforms that we're going to see how much of the lunar night we survive, and they're working to get to that goal, but they don't don't believe they'll hit it on the first try.
Is there for your independent network, not for a unit that plugs into somebody else's hardware, form factor, mission purpose, whatever, is there a critical mass, like a number of nodes or something that you need to put up there, or is one enough?
On the theory that some is better than none, no. On the thing that we used to say back in the Marine Corps, because we like to keep the numbers nice and simple, 1 from 1 is 0, 1 from 2 is 1.
Mm-hmm.
So having redundancy is always a good thing to have.
Mm-hmm.
So there's a point at which you're saying everything will be fine as long as everything is fine.
Yeah.
As soon as something goes wrong, everything just went wrong.
Mm-hmm.
So we would much rather have some sort of redundancy. If you're going with that single blade architecture, we would honestly rather have 2 of those. There's also the possibility that the event that kills one kills both, in which case 2 from 2 is 0.
Yeah.
But in that case, 3 from 3 would also be 0. So yeah, there's this is a new technology. We're working on building up at least ground heritage to the point where we can say with X levels of testing, we've had X results for X time. We feel that with this environment, which is analogous to low Earth orbit, which is the easiest, the most hospitable of all the space environments, low Earth orbit is. We should be able to last our 3 to 5 years, just like the sticker says. So that's kind of the goal. Build up the confidence among the community that this will do what it says it needs to do. Are we going to guarantee that this thing can keep processing on the very first iteration right through a massive solar storm, a coronal mass ejection? No. And frankly, for production models, we don't want to deliver that degree of reliability. What we actually want to do is know that such a thing is coming, shut everything down before it hits us, and just ride it out and come back on with minimal or no damage after the fact.
Okay. We've talked about the data pipeline of the requirement for data to come in through the DSN and that. We're looking at a cislunar economy. I don't know how far out that is. We talk to people all the time, but what timeline could we be looking at for that?
Me neither. 3-5 years ago, I would have said 20 years.
Mm-hmm.
Today, I would feel 10, maybe. We can have that. We can have a fairly developed cislunar economy in 10 years if there is the desire. We're apparently back into the great game realm of politics, where we have kind of a bipolar world. I'm starting to feel like this is the Athenian League and the Delian League, where we apparently are going to play Athens. Some people would say we'd be Sparta, but I'd say that we're probably more Athens in this scenario, as China starts to get as militarized as we are. So yeah, there's arguments to be made on all sides of that. So as we get into that, and there's the great game, if we can do like we did with the Soviets again, and have this a competition of science rather than a conflict of the historic variety, then humanity will be better off. I am confident that the more players we can have involved, not just the US and China, but I'm thinking Europe. I'm also having some conversations with some of the Latin American space companies and individuals who are Latin American like myself and who work in the space industry. I feel that leaving that part of the world behind, in Africa and the rest of Asia that is not Japan and India and China, that would be a bit of a disservice to humanity. And I feel that we will be greatly ahead the more of us that can be involved in this new race. Everybody, I believe, has something to contribute, and there's a heck of a lot more space above those clouds I see than there is below them. Okay. So I believe that it can be a boon to humanity in every way possible, to include, why do you need to struggle for land here on Earth when there's so much? There are realms above our heads.
Yeah, let's make some real estate. What kind of anecdotal evidence have you heard lately demonstrating that you can see people recognizing that there's this impending data problem, right? But talking about that shift that I mentioned at the beginning.
Well, let's see now. I've been evangelizing this thing for 2 years now. In that time, I have had initially a lot of space people tell me, why do we need this? We've gotten this far without it. The very first people who got it, who really saw it, were people with a computing background. People who had worked in data centers, people who had worked edge solutions, people who had worked autonomy, people who worked in the mining industry. That was the first group of people who said, yes, we have an insatiable desire for data that simply doesn't exist in space because everybody knows you can't. So if you change that to you can, then that's going to be an insatiable desire for data as well. In that 2 years, I've had the same conversation with the same person 3 times in a row, and 2 or 3 of those times they have said, I don't get the utility in what you're saying. I don't know why it's necessary. And then in multiple cases, really in the past 6 months, some in the past year, but a lot of it's been in the past 6 months. Some of it even in the past 6 weeks. People who have previously said, I don't know why this is necessary, have come back to me and said, so we have a data problem and we really need a way to handle that. And you might have the solution to that. Some of that, I believe, is just a matter of, putting the earworm in there and it kind of wiggles its way in and it takes hold. And then, like you said earlier, where once I pointed out the thing to you, then you saw all the
right news articles and whatever
about the DSN. Yeah. And it's like saying, here's my premise, and then your mind is primed to look for the examples that illustrate that premise or refute it. And I think these folks are seeing, and here's our problem with data, and this is just an insurmountable thing. There's no way around it. And that little earworm that got stuck in there a few months back says there might be a way around it. Let's find out if this guy is legit. Let's find out if this offering is real. If it can do what he says it can do. Some of it's that. I think another part of it is Artemis. People have started to allow themselves to think bigger.
Mm-hmm.
A year ago, I would not have told you about, if I was pitching to you, I would not have made a big deal about autonomous operation, space assembly, manufacturing, laboratories, space stations,
Mm-hmm.
autonomous robots on the moon and asteroids. I wouldn't have told you about that stuff, because if I did, that would turn me into a sci-fi nut. And it's like, okay, Rick's got a cool science project.
Right.
I hope he writes a book about it, because it's never going to happen in real life. And over the past 6 months, again, through conversations, and really I saw it with the Space Symposium in Colorado Springs, which was at the end of August, and SAT Show, which was last week in DC.
Right. And it's mid-September now.
Yeah,
we're recording this.
Yeah, it's mid-September now. So I saw in those contexts, people are talking freely about the cislunar economy. They're talking about, okay, so we're going to need this capability. This company over there is working on this system that we'll need. This company over there is working on this. This company's got a proposal for this other thing, and it's starting to come together. And like, you're seeing the Lego bricks there, and some of them are already stuck together. And yeah, they're talking about what sort of data problems there are. They're running into these problems about, wait, you want us to not use the DSN? We don't have a fully established moon to earth communications network. What are we going to do with all this stuff? We need to have rovers that are traveling kilometers per day, so they can actually hoover up enough material to generate the propellant that we need. I did a little bit of a nod to the Canadians there with the hoovering. So yeah, they're starting to recognize that this is a real data problem that needs to be addressed yesterday. This went from a hypothetical thing 10 to 15 years from now to, oh my God, we are in trouble.
Well, and the pressure that's being applied on that system, right? With all the new satellites being thrown up, and it's one thing to talk about it like 2 years ago or something, right? SpaceX is going to make Starlink and keep throwing up all these satellites. But when it actually happens and the satellites are there and you watch them launch, and in 25 minutes, 60 new satellites are flying around, right?
And you're like, oh,
how's this going to work?
We just doubled the population of satellites in low Earth orbit in 2 years. And we might do it again in 2 to 3 years. And it's
how
like,
are we going to handle this?
How does this even work? That's where Mariba Jah, he's been the canary about space situational awareness, and everybody's listening to the canary now.
Yeah, I feel that you and he have gone through similar paths of big, Chicken Little, the sky's falling.
Yeah,
I use you two as examples all the time when I'm talking to other people about, look, there's fashion in this stuff, right? Something's in fashion, it's out of fashion, and then pressure gets applied, and then suddenly everybody realizes, oh, we obviously need this. Well, you didn't say that 6 months ago, pal.
Yeah, it's kind of like our current air traffic control system is a guy in a tower with binoculars and a handheld radio, and he's at Dulles, and they're handling thousands of airplanes a day, but nobody's crashed into each other yet, so everything's okay.
Yeah,
and that's kind of where we are in terms of SSA. Like, it is, and honestly, so much of the space infrastructure. I was just hearing about another system. When I was an outsider to the space industry, I assumed everything was highly developed and done by professionals and like super streamlined and optimized. And
then you start talking to people.
Yeah.
Find out it's duct taped together with spit and glue. And
yes. So many things are like, some guy in 1975 saw that X is a problem, and as a Band-Aid patch that he never expected to exist for more than 6 years, he made a suggestion. then somebody wrote that suggestion down, and now it is enshrined,
right,
and inviolable.
mm-hmm.
And he has since, like, you know, if I thought about that like 15 more minutes, I probably would have come up with something better. And
Right.
we're lashed to this solution that is older than most of the people working the problem.
Right. Right. This kind of process improvement problem, right? Of the well, we've always done it this way, is the kind of thing like, this is a process improvement company, Cold Star. It drives me berserk, right? We need to be willing to look at new ideas, people. You know,
why does this process exist? What does it do? What was the climate in which it was created?
Mm-hmm.
How is the climate different today?
Yeah.
Like, that is frankly stuff that you should be analyzing for all your processes every few years.
Yep.
And realistically, if you're doing a space company right now, if you don't want to get caught out in the wind, you really need to look at things and say, how are we going to operate with X, Y, and Z changes in the next 5 years?
Mm-hmm.
And I would identify, not all inclusive, but I would say, let's look at another halving of launch costs.
Mm-hmm.
Let's look at a doubling of the constellations in orbit or more. And let's look at regular cislunar activity from this point forward. And I'm projecting forward 5 years.
Right.
And I'm saying that if maybe that has nothing to do with your business model or the way you do things or operationally, but if you haven't looked at that set of problems,
Mm-hmm.
you're going to have a bad time.
Yeah, you're going to get blindsided by new developments because you'll have designed a solution for a problem that's out of date now. And folks, I want to remind you, as we go farther out into the solar system, to Mars, the asteroid belt, and that, some guy or a person flying a drone here on Earth, out there in the asteroid belt to do asteroid mining is not good enough. As the drone gets closer to, I knew this in 2014. as the drone gets closer and closer to the asteroid, which has its spin, pitch, yaw, and all that stuff, right? It's got to make adjustments now, and it can't wait 1 or 2 seconds for the human to go, uh-oh, it's going to crash into this thing. It needs to have a little AI on board and the processing power through edge computing to be able to make that decision itself and make the adjustment, right? And we need good simulations in order to be able to do this. So that's a problem that I see coming down the field. So let's explain.
Ironically,
go ahead, Rick.
Ironically, that is the very genesis of OrbitsEdge creation. I was a deep space industries guy, as you recall, and I first came at this from autonomous mining robots, and I was like, joystick doesn't work. The computers we have don't work, and doing a part 3 of the computers that we already have doesn't really do anything fundamental. So let's do this thing so we can have decent computers on into the future.
Yep. You know, I'm on board. Let's explain compute as a service as the business model, right? You want to put up a network, or a constellation, I guess, of edge computing satellites. Who's the customer for this thing? How does it generate revenue, right? How does it pay for itself?
Yeah, so if you use AWS services, I'm not going to say that you get nickel and dimed, but if you do a thing, there's money involved. If you do computation, there's a little bit of money goes there. If you do some storage, a little bit of money goes there. If you relay it from place A to B, you take it in, you put it out, there's a little bit of money right there. We're essentially looking at doing the same thing. If you need to load up a program on our platform, well, there's money there. If you want to build and maintain a database of X size and do updates to it, and like we were talking about that Earth observation thing, if you're wanting to do a change analysis style database, you have pictures of the entire Earth. Like, that is well, not the entire Earth, the entire land area of the Earth. So yeah, if you want to do that, there's a bit of money involved. So one of the issues with Earth observation right now is, so the great thing for the economics of Earth observation is it's pretty cheap and easy to put up a constellation to do picture taking. The bad part about the economics for Earth observation is it's pretty cheap and easy to put up a constellation to do picture taking. So you don't have like one or two players, you have like a half a dozen plus players, and they're all going after the same market, which means they're kind of in a race for commoditization. They're kind of all chasing the same dollar, and the money is getting harder and harder to find, where some of the companies are even like, I don't know, let's just throw it up there for free and see if people want it. Like they're running into some serious economic problems. So we're proposing yet another cost for it to deal with that. Yeah, what we're looking at is adding a sort of differentiator for someone, or more essentially what they're doing is delivering a lot of haystacks, and we are interested in delivering needles. So I guess that's really what we're trying to say here. We're trying to say we want to deliver more quality data instead of just more data.
The vital few data points instead of repeat shots of the same waterway or something over and over, or cornfield or something like that, right? And here's what changed. You know, is this of interest to you?
And there's also like hyperspectroscopy or hyperspectral is coming into the vogue. You've got the IR, the UV, the specific colors of the rainbow. They're getting more discerning in the amount and types of data that they're capturing now. And one of the things that you're starting to see is multispectral imaging, where you're actually getting an idea of the chemical composition of what you're looking at. And that can help you determine whether you have soybeans or weeds in this field, how well it's watered, how mature fruits or seeds or crop is. It gives you a lot of information for that sort of thing, not just crops, but also for forestry, forest management. There's some very interesting things that we're looking at involving a rhino charity. It's about tracking rhinos obviously in Africa. They're easier to track in Africa than they are in the other continents for some reason. They just seem to show up better. So yeah, there's some interesting things where you can track rhinos, and you can possibly detect if a rhino's been hurt or injured or sick or dead. You can also extrapolate that to other sorts of wildlife. You can do other sorts of wildlife tracking. That all depends on resolution, along with algorithms that can do the actual tracking, can do recognition, object recognition, and track individual herds over time. You could learn more about behaviors of animals that are not as well known. An interesting thing is one of our naval analytics packages is basically not clouds, not water, and that would capture everything that is not clouds, not water. So that is cargo vessels, fishing fleets, trash in the middle of the ocean, or if there's a pod of whales that has surfaced. Now, those repeated hits over time would be a pretty good proxy for migration patterns. And it would also be a fair way with an analytics package to track individual pods of whales. You could basically get a whale census, like a day-to-day whale census. You would find out about
breed
catting
sometime.
Yeah.
Huh.
You're not going to capture 100% of their breaches, but you're going to capture some fraction of them. And with that, knowing rates of speed, probable course heading, you can do a fair bit of extrapolation. And also whales are an indicator of the health of the ocean itself. So where they're going is probably where there's food for them. So that sort of thing kind of like circles back and ties back into everything. And we feel that that is tremendously useful. Oh, the reason I mentioned the spectroscopy earlier, one of the, this is great, but there's no money in it, things is I have a huge fascination with dinosaurs. Well, the stone that makes up the dinosaur fossils is different from the surrounding area stone. So that might possibly show up in the right sort of spectroscopy. And we're talking passive, not active. So that's a little bit harder for stone. It's a little bit easier for things like plants, but it with the proper resolution, it might be possible to pick up large dinosaur bones. And with fossils like that, you have, it's covered by the ground, it's covered by the mountain, but then you have erosion, which uncovers it, but then you have erosion, which also turns it into dust. So there's a limited period of time in which a fossil is exposed but not destroyed. And if you could have a satellite that just drops pins across the earth, as I don't care if half of them are false. If that half of them are false hits, if half of them are real, it'd still be a tremendous boon.
I'm thinking about funding for that. how that could work. There's
the Nat Geo
charity
angle.
There's people wanting to give back and gifting. So the key is to have some capability up there first, right? And and then be able to do it.
What we're basically saying is, let's build a piece of infrastructure. Let's build a thing that can do the things. And since it's general purpose computing, people will put it to general purposes. It's not something that is an application specific platform. It's good at one thing and very good at one thing and useless for anything else. We specifically want to do general purpose computing initially. Later on, we definitely see the utility of ASICs for specific tasks. You want, this one's going to do nothing but image analysis. Okay, we can do that. This one's going to do nothing but packet switching for communications nodes. That's doable too. This one's going to do Specialization can come later. Right now, we're focused on the general capability.
Okay. What is OrbitsEdge intention to do next? What's the next step? I think we'll finish up on this question.
We are currently agitating, rabble rousing, and working towards getting a mission with the ISS National Labs. That is conversations with Hewlett Packard Enterprise. So they have their Spaceborne 2 computer up there. It follows on, as you might imagine, on the heels of Spaceborne 1. And they've both been very successful. They're both they were both operational inside the ISS. 2 is currently there. They're using it to do processing on some of the experiments that are currently running on the ISS. And our special intellectual property is the radiation shielding, thermal management, and overwatch system. What we would like to do is do something in conjunction with HPE and ISS National Labs to carry this outside. We want to take that capability, what exists on the ISS, and demonstrate that it can work outside the ISS. So that is our entire intent on this. We want to fly Spaceborne 3, as we're calling it, going outside.
Okay, sounds very cool. And
yeah,
if and when that happens, come on back. We'll talk about it.
We're working on it. We're working all the things. Gosh, if you have a moment,
sure.
We'll have to crop this part out. I've got a mission patch for it. In fact, I'll show you my my drinking vessel that I got at Symposium from HPE. So this is HPE's sticker. Says my other computer's in space. It's commemorating Spaceborne 2. And these are various
Redwire
friends
Virginia
and whatnot.
Space. Yeah.
Virginia Space, because that's when I went to Virginia for the mission that took this thing into space. But this is our mission patch. This is for Spaceborne 3. It says taking the edge to space, mission 2022. Humanizing space for all mankind. In order to humanize space, we must first commercialize space. To commercialize space, we must compute in space. Edge computing is fundamental to us humanizing space for all mankind.
Very cool. And I'll try and do a screenshot of that for the audio version as well.
I will.
If I forget,
I'll try and
please remind me, folks.
Yeah, I've got some that are not actually on things. So I'll have to take a picture of that.
Okay, and we'll upload that. Well, thank you, Rick. How can people find out more about OrbitsEdge and get a hold of you if they want to talk further?
Well, we have OrbitsEdge.com, obviously, and we have OrbitsEdge on LinkedIn and Twitter. We're more active on the LinkedIn. We're working on getting more active on our YouTube. That's a priority that has not yet happened. And personally, I am findable on LinkedIn as Richard J. Ward. Where you do the type in the linkedin.com / whatever. I'm actually Richard J. Ward on that.
All right.
So I'm LinkedIn
Sounds
OG,
good.
I guess.
All right. Well, thank you, folks, for listening to two ENTPs prattle on edge computing. Rick, thanks for doing this. I know you were at the SpaceX launch last night, back home late, up early. We're both sleepy.
It was fantastic.
Got a lot to do.
I gotta say, Inspiration 4 was a well-named mission. The outpouring that I've seen from the space community, obviously there's going to be the people who say, how can you do this when there are so many things wrong with the Earth? If that's your position, then I suggest you stop watching all movies, because $200 million is an average movie budget. That's not even a big movie.
Right.
So if that's your problem, then you should probably just boycott all of humanity.
Right. And let me finish up, Rick, by saying thank you for wearing the Cold Star hat. I sent Rick a hat. He was one of the first 6 people or 8 people or something I sent the first batch out to. If you're listening or watching and you want one of these hats and you'll actually wear it, that's the caveat. They cost money, you know. I will send you one. Just shoot me an email or a message on LinkedIn with your address, and I'll be happy to send you one.
I will wear this in numerous places.
All right. Thank you very much. Thanks for joining Rick and I for today's show. If you're interested in learning about edge computing, connect up with Rick. I suggest you do it through LinkedIn and check out the OrbitsEdge website. If you are a defense contractor or space company who is actively looking to develop a commercial side to your business, i.e. not having the government as your sole customer, come and talk to us at Cold Star Tech. There are values, principles, processes, a whole bunch of things, mentality, a whole different shift that you're going to have to make, your people are going to have to make. If you try doing the same things that you've been doing that have made you successful as a defense contractor, out here in the commercial world, you will fail. It doesn't work the same way. And so you can take a lot of time off solving this problem, shave it off by working with us and have a much easier time. Come on over and talk to us at Cold Start Tech. Thanks for listening.